Well, I'm ready to show you all something that ties in our last few sets of topics. So when we began with functions of multiple variables, it didn't take us long to get to partial derivatives, and now we've just ventured through some applications that all involve partial derivatives, and they all have sort of a similar flair or look to them. And in each of these cases, we were assuming a function of x and y only, but we have discovered by now that you could have more variables. And it's possible to rewrite each of these as a dot product. So for the total differential, it could be this dot product. And please remember that this is a shorthand. Technically, it's the x partial derivative of the function f of xy. But when you write it fully every single time, it fills up this paper is one of the major problems. But sometimes we get what I call parentheses blindness, and we stop seeing what is key, the partial derivative of the function here. And we have the chain rule, which could be used to measure something different. But again, it was the dot product of a vector that had the partial derivatives in it with, in this case, dx dt, dy dt. And for the directional derivative, again, more of the same, dot product x partial derivative, y partial derivative with the vector u1, u2 are the components, or simply called the vector u, which was a unit vector. Now, there's a name for those, a shorthand that refers to when we calculate a vector of all those partial derivatives. I'll write that, don't panic. And the name for it is called gradient. The gradient of a function, the gradient, this is our notation for gradient. You can find in the book that we're using if you're in my class, but you can also find it by searching online, that it does have a nickname. This symbol here can be said as del, del. I've never called it that. I never even knew there was a name for it for my earlier part of my schooling. We just knew that was called gradient, so we called it gradient. So the gradient of a function is a vector you get of the partial derivatives. So it is a vector of the partial derivatives. Let's make that a capital P. It's important. And if you had a function of three variables, f of x, y, z, then the gradient of that function would be vector with x partial derivative, y partial derivative, z partial derivative. Okay? So far so good? Let's do some examples of calculating the gradient of a function. So again, we're going from something that had applications to them to just a calculation for a moment until we get a little bit farther into it. So, first example. It's going to be fun. If f of xy is equal to x squared minus e to the 2x cosine of y, the gradient of that function will be a vector with two components because there are two variables in the function. Again, I'm getting a little bit lazy here and not writing in the formal notation all the time. My apologies to the purists who are visiting my site. So gradient f of xy, so we need the x partial derivative. Well, the derivative of x squared, hey, that's my favorite, 2x. And if x is the variable, that means cosine y is nothing more than a constant, so I just need to find the derivative of e to the 2x, which is 2 times e to the 2x. Cosine y is a constant there. So then the y partial derivative, the derivative of x squared is 0, and the e to the 2x is a constant. And the derivative of cosine of y would be negative sine y. But I'm going to put a plus sign here just so you know that the negative from this derivative and the negative from this derivative, that I actually was thinking about it. You wouldn't generally write that down in your solution that you turn in, but I'm writing it here so you know that I didn't miss something. Alright, pretty straightforward. What is it used for? Well, I don't know, we're math robots. We're just calculating until the next video. Okay, here comes the next example. F of x, y, z is x squared plus y cubed plus z to the 4th. This is a function that who knows what it's used to measure, but when we calculate the gradient of this function, we will be creating a vector that has 3 components because there were 3 variables in the original function. And what is the x partial derivative? I can almost hear you say 2x. And the y partial derivative? Oh, I definitely heard you that time. 3y squared. And that would be 4z to the 3rd. What's it used for? Well, you've just seen that this is the front end of a series of other formulas that could easily be rewritten with gradient in front of them. One more little example, and this is more about practicing partial derivatives if you haven't figured it out. We have a function of x and y, and it is y multiplied by sine of xy. The gradient of that function is going to be a vector that has 2 components, the x partial derivative and the y partial derivative. The x partial derivative. Well, you might think of this statement here as the same as like 8 sine 8x, where the 8 here is a constant, and it's like the variable y, because y is a constant in this problem. And if you were going to find the derivative of this, you know what the derivative of sine is. That's probably not where our issue is going to come up. The issue is going to be, what do we do with all the y variables? Well, the derivative of sine of 8x would be 8 times this. But there's another 8 here, so that's 8 times 8, or 8 squared. So y times y is y squared, cosine of xy, or 8x. So it would be 8 times 8 cosine 8x if y were the constant. Comma, second component. Uh-oh, now y is the variable. So this problem, maybe I should think of it as y sine 2y. So x is now my constant. There is a product here a multiplication of two functions of y. I have to basically find the derivative of y, which is 1, leave sine of xy alone, plus leave y alone, and now take the derivative of sine of xy, which would be cosine of xy times, if y is the variable, derivative of y is 1. That'll leave me an x, or a 2 in this case. Now, what I did here was perhaps a little too fast of a mental or an out loud computation for some of you. I would strongly suggest finding the product rule derivative here, writing it out, and wherever you see the number 2, you write in an x in this solution if you're struggling with the variable versus the constant concept. Although I wouldn't be upset if you turned it in this way. It's almost guaranteed that a solutions guide would go to here, sine xy plus xy cosine of xy. Now if you stick around to the next segment, we will look at a use of the gradient as a tool by itself. So stick around.